China's goal of 1 hour global travel now seems less like science fiction.
In recent years, China has made significant strides in revolutionizing aviation. They have built not one but two fifth-generation warplanes, the J20 and J31, and have also produced an arsenal of unstoppable hypersonic missiles. Now, the Dragon country wants to kick things up a notch. China has unveiled a new $13 billion aircraft that defies all laws of physics. Using hypersonic jet technology, China aims to push the boundaries of global air travel, offering unprecedented speeds and capabilities that could drastically shorten travel times and reshape the way we think about flying. And of course, it will inevitably find specialized military applications for this technology. So what has China done so far, and what remains to be done? Let's find out together. Hypersonic travel and the Nankiang No. 1 hypersonic travel promises to fundamentally transform the future of global aviation. At its core, this technology focuses on achieving speeds beyond Mach 5, which is 5 times the speed of sound, with the potential to revolutionize both air and space travel. One of the most ambitious goals within hypersonic technology is point-to-space travel, a concept that involves aircraft reaching the edge of space and then re-entering the Earth's atmosphere, drastically reducing flight times between far-flung destinations. With this technology, a flight from New York to Beijing, typically a 14-hour journey, could be completed in under 2 hours. Well, guess what? China has set its eyes on his lofty goal. Their answer to the challenge is the Nankiang No. 1. In 2023, this experimental jet reached an astonishing Mach 6, a speed that marks a significant milestone in the pursuit of hypersonic flight. Designed by China's state-owned aerospace giants, the Nankiang No. 1 is equipped with cutting-edge engines and materials capable of withstanding the extreme heat and pressures generated at such speeds. This accomplishment places China at the forefront of hypersonic technology, competing with other nations like the United States and Russia, which are also working on similar developments. China's aspiration to dominate hypersonic technology is evident in its continuous investments and strategic partnerships. The nation's ambitious goals for hypersonic technology go beyond just advancing air travel. They aim to secure a dominant role in the next phase of the global aerospace industry, influencing everything from military defense to commercial space exploration. Hypersonic flight speeds, which are Mach 5 or higher, represent a new frontier in aviation technology. At Mach 6, an aircraft can travel at an incredible 4,600 miles per hour. This speed allows for travel between distant cities in a fraction of the time it currently takes. For instance, a flight from New York to London, typically a 7-hour journey, could be completed in under an hour with hypersonic technology. This radical reduction in flight time would redefine long-haul travel, making it possible to journey across continents or even oceans in mere minutes. To achieve these extraordinary speeds, hypersonic aircraft rely on a sophisticated and multi-stage propulsion system that combines multiple types of engines to optimize performance at different phases of flight. Traditional jet engines, like turbofans, work efficiently at lower speeds and altitudes, but are not capable of reaching hypersonic velocities. At speeds beyond Mach 5, aircraft need specialized propulsion systems. The hybrid propulsion system in hypersonic flight typically includes turbofan engines for takeoff and subsonic flight, ramjets to transition through the high-speed regime, and rocket engines for the final push into hypersonic speeds. Turbofan engines, often used in commercial jets, are essential for the early stages of flight, providing the necessary thrust to get the aircraft off the ground. As the aircraft accelerates and reaches higher altitudes, the transition to ramjets becomes necessary. Ramjets are designed to operate efficiently at supersonic and hypersonic speeds by compressing incoming air before mixing it with fuel and igniting it, creating a high-pressure explosion that propels the vehicle forward. Once the vehicle reaches hypersonic speeds, rocket engines take over, providing the additional thrust needed to maintain Mach 6 and beyond. But this is easier said than done. Engine technology and challenges. One of the most innovative propulsion systems currently being explored for hypersonic flight technology is the multi-ducted twin-turbine ejector ramjet. Shortened as the Mutter engine, This advanced engine is a hybrid propulsion system that combines multiple elements of existing engine technologies to optimize performance at different phases of flight. By incorporating elements of turbofan, ramjet, and rocket engine technologies, the Mutter engine aims to address the complex demands of achieving speeds up to Mach 6 and beyond. At the beginning of a hypersonic journey, conventional turbofan engines are still essential for getting an aircraft off the ground and through the subsonic phase. Turbofan engines are widely used in current commercial jets because of their efficiency in providing thrust at low speeds. These engines work by using a fan to draw in air, which is compressed by a series of stages before being mixed with fuel and ignited in the combustion chamber. The expanding gases are then expelled through a turbine, which powers the fan, and the exhaust provides the thrust. At subsonic speeds, turbofans are the optimal choice due to their high efficiency in converting fuel into thrust. For hypersonic aircraft, turbofans operate well for takeoff and the early stages of flight. However, once the aircraft approaches supersonic speeds of Mach 1 and beyond, the turbofan's efficiency starts to diminish due to the increasing air resistance and drag at these high velocities. This is where other propulsion systems come into play. Here, the ramjet engine takes over by using the aircraft's forward speed to compress incoming air without any moving parts. The compressed air is then mixed with fuel, ignited, and expelled through the nozzle to create thrust. This process allows the engine to operate efficiently at supersonic and hypersonic speeds. Ramjets are designed to function at velocities starting at Mach 3 and extending into the hypersonic range, making them ideal for high-speed flight. At hypersonic speeds of Mach 5 to Mach 6, the ramjet's efficiency is maximized, but maintaining the flow of air and ensuring proper combustion becomes increasingly difficult as the engine experiences extreme pressures and temperatures. The Mutter engine takes advantage of this by incorporating multiple ducts and ejectors that help maintain airflow stability at higher speeds, significantly reducing the risk of flow separation that can occur in traditional ramjets. For example, the scramjet, a variant of the ramjet, has been used in experimental vehicles like NASA's X-43A, which reached speeds of Mach 9.6. Scramjets can operate at even higher speeds than conventional ramjets by keeping the airflow supersonic throughout the combustion process, but they still face challenges related to fuel mixing and thermal management at extreme speeds. To achieve the transition from supersonic to hypersonic speeds, rocket engines are often employed. Rocket engines, unlike jet engines, carry both fuel and oxidizer, allowing them to operate at altitudes where atmospheric oxygen is scarce or non-existent. These engines are ideal for giving the aircraft that extra push it needs to reach speeds beyond what a ramjet can achieve. Rocket engines are crucial for the final acceleration phase, particularly in hypersonic travel, where aircraft often exit the atmosphere or operate in near-space environments. Once an aircraft has reached high supersonic speeds, rocket engines are used to deliver the additional thrust needed to reach and maintain hypersonic velocities. One of the most notable examples of rocket engines in hypersonic flight is the Space Shuttle's main engines, or the X-15 rocket plane. The Space Shuttle used a combination of turbojet engines for takeoff and rocket engines for space travel. But perhaps the most significant challenge in hypersonic flight is heat management. At Mach 6 and beyond, friction with the atmosphere generates extreme temperatures that can cause catastrophic damage to aircraft. As an aircraft reaches these speeds, the air compresses ahead of it and heats up due to the shock waves formed by the high-speed airflow. This leads to temperatures on the surface of the aircraft that can exceed 2000 degrees centigrade, which is hot enough to melt or warp conventional materials. To address this, thermal protection systems and advanced materials are being developed that can withstand the intense heat generated during hypersonic flight. For example, the X-43A employed a lightweight carbon-carbon composite material, which is highly resistant to heat. The Mutter engine and other advanced propulsion systems integrate active cooling techniques, such as liquid cooling of engine parts and the use of heat-resistant coatings to prevent engine components from overheating. Engine designers also focus on maintaining engine stability at these extreme speeds. One approach involves using re-entry technology adapted from space exploration, where aircraft and spacecraft are designed to maintain a steady temperature and prevent damage during high-speed re-entry into the atmosphere. This technology can be used to ensure that propulsion systems like the Mutter engine continue to operate efficiently at speeds that would otherwise cause catastrophic failure. So what do we know about the capability of the Mutter engine and others like it so far? Testing and future operations. In the early phases of hypersonic research, unmanned prototype aircraft have played a crucial role in validating key technologies that are essential for high-speed flight. These prototypes are designed to simulate the extreme conditions of hypersonic speeds and test the limits of propulsion systems, heat management, and aerodynamic performance. During one of the most notable tests, a small-scale version of the Nankiang No. 1 was launched in 2023, reaching speeds of Mach 5.8 in a controlled flight test. This success provided invaluable data about the aircraft's aerodynamics, its multi-stage propulsion system, and heat management strategies. In addition to speed, the unmanned tests were also designed to assess the aircraft's ability to handle the extreme pressures, temperatures, and mechanical stresses associated with hypersonic flight. The results of these tests have been overwhelmingly positive, demonstrating that the foundational technology is sound. Looking forward, China is on track to achieve full operational status for its hypersonic aircraft by 2025. This timeline represents a significant leap in the development of commercial hypersonic travel. When it comes to passenger service, the Nankiang No. 1 holds the promise of transforming air travel as we know it. Initially designed with unmanned prototypes, the full-scale aircraft will be capable of carrying passengers at speeds never before imagined in commercial aviation. The ability to travel from New York to London in under an hour, or from Beijing to Los Angeles in just a few hours, opens up entirely new possibilities for high-end travel. Business executives in particular stand to benefit immensely from this new class of travel, as hypersonic flights could allow them to complete long-haul flights in a fraction of the time it currently takes, while also offering luxury-level amenities on board. But it's not a bed of roses. Noise issues and sonic boom. The push for hypersonic flight promises to revolutionize air travel, but with it comes a significant challenge: noise pollution, specifically from sonic booms. As aircraft break the sound barrier, the explosive sound of a sonic boom, created by the shockwaves produced when an object exceeds the speed of sound, can cause disturbances in populated areas. This issue, long recognized in the supersonic era, is set to become even more pronounced as hypersonic jets approach and exceed Mach 5 speeds. At speeds above Mach 1, the aircraft creates shockwaves that generate a sonic boom, a sound so intense that it can be heard miles away. This is a direct consequence of an aircraft surpassing the speed of sound, causing the air to compress rapidly and release energy. While supersonic flights such as the Concorde were designed to minimize this disturbance, the problem remains significant. For example, Concorde, which could reach speeds of Mach 2, was known for its sonic boom, which was loud enough to rattle windows and disturb entire neighborhoods. The disruptive effects of this noise were a major factor in the aircraft's ban in several countries. Airports in the United States, for instance, refused to grant Concorde commercial flight permissions because the boom was too disruptive to residents near flight paths. This ban on overland supersonic flights restricted Concorde's potential for greater profitability, confining it to transatlantic routes that could fly over oceans where the sonic boom wouldn't cause the same disturbances. With hypersonic jets, which will travel at speeds over Mach 5, the sonic boom will not only persist, but could be even louder. As aircraft speed increases, the shockwaves become more pronounced, meaning that hypersonic travel could lead to a more intense and pervasive sonic boom than what was experienced during the supersonic era. NASA has been actively engaged in efforts to reduce the disruptive nature of sonic booms. One of its most ambitious projects is the X-59 Quiet Supersonic Transport, a prototype aircraft designed to reduce the sonic boom to a soft thump, far less jarring than the traditional boom. The X-59 is part of NASA's Quiet Supersonic Technology, or QUEST program, which aims to make supersonic and eventually hypersonic flight more feasible for commercial use. The X-59 incorporates a design specifically engineered to minimize shockwaves. Unlike conventional supersonic aircraft, The X-59 features a long, slender fuselage with a narrower nose and reduced wing sweep. These design elements are intended to disperse the shockwaves generated at supersonic speeds, reducing noise pollution. While the project holds great promise for future commercial aviation, the technology remains in development, and its success is not guaranteed. The challenge of reducing sonic booms from Mach 5 to something as mild as a thump remains a significant hurdle for researchers. However, even if the X-59 proves successful in its design and testing, there are still numerous obstacles to widespread adoption. For one, to be standardized across the hypersonic fleet, and commercial aircraft would have to meet stringent noise regulations to gain approval for overland travel. The reality is that while the X-59 can significantly reduce noise, achieving complete sonic boom-free hypersonic flight is still an ongoing challenge. The issue of noise pollution from sonic booms will likely lead to significant regulatory hurdles for hypersonic aircraft. The Federal Aviation Administration, for example, has regulations that prohibit supersonic flights over the United States. If hypersonic jets produce even louder booms, these regulations could become even more stringent. In addition to regulatory challenges, the commercial viability of hypersonic flights could be directly impacted by noise restrictions. If hypersonic jets are only allowed to fly over oceans or remote areas, the routes available to airlines would be significantly limited. For airlines hoping to operate profitable, high-speed commercial services, the cost and time to fly only on certain routes could undermine the business model, as many of the most lucrative flights are overland. Cities that stand to benefit most from fast travel times might find themselves excluded from this transport revolution. But we're not done with the issues just yet. Heat and thermal protection. As aircraft push through the air at over 3,800 miles per hour, the friction between the craft and air molecules leads to an extraordinary buildup of heat. At these velocities, the air is compressed and heated before it even makes contact with the aircraft, generating immense thermal energy. This results in surface temperatures that soar to 2,500 degrees Celsius or more, far exceeding the heat levels faced by conventional supersonic jets. For context, the Space Shuttle faced temperatures of about 1,500 degrees Celsius during re-entry, which is already significantly less than those generated by hypersonic vehicles. The immense friction can permeate deeper into the aircraft, threatening its structural integrity. The outer layers of the aircraft, typically made from advanced alloys, are forced to withstand the continuous heat buildup. Without effective thermal protection, these materials could soften, warp, or even melt, endangering the entire flight. The high heat loads are not confined to the outer shell alone. The internal components, including fuel tanks, avionics, and engines, are equally susceptible to damage. Even a minor miscalculation in heat distribution or inadequate protection can result in catastrophic failure. For example, during the development of the Boeing X-51 Waverider, which successfully reached speeds of Mach 5, the team had to address the risk of structural damage from thermal loads. As the X-51 approached its hypersonic velocity, heat built up on its surface and threatened to compromise its design, forcing engineers to rethink the material choices and cooling systems used in the aircraft. To mitigate these risks, aerospace engineers are developing advanced materials that can withstand extreme heat. One key development is the use of ceramic matrix composites, or CMCs. These materials combine ceramics with fibers to enhance strength and are preferred for their exceptional heat resistance. CMCs can endure the extreme temperatures generated at hypersonic speeds without degrading or failing. While passive cooling technologies, such as heat shields and reflective coatings, can help manage heat on a short-term basis, hypersonic travel presents a unique challenge: how to manage heat over long durations. Unlike spacecraft, which only experience extreme temperatures for short bursts during re-entry, hypersonic aircraft need to handle continuous heat generation during extended flight durations. This means that passive cooling systems that have worked for supersonic aircraft are inadequate for hypersonic conditions. Traditional cooling methods, like liquid cooling or air cooling, are insufficient for the heat loads seen at Mach 5 and higher. Active cooling systems, such as cryogenic fuels or heat-exchanging systems, must be integrated into the aircraft's design. One solution explored for both hypersonic aircraft and re-entry vehicles is using the fuel itself as a coolant, a method known as fuel cooling. As the aircraft flies, the fuel circulates through specialized channels near the hot surfaces, absorbing heat before it enters the engine combustion chambers. However, predicting heat buildup and maintaining aerodynamic shifts during flight is still an ongoing challenge. Aerodynamic changes, such as those caused by altitude variations and flight speed fluctuations, can cause localized areas of extreme heat, which must be managed without compromising flight performance. Inconsistent heat distribution can cause unwanted stresses and potentially catastrophic thermal failures. In addition to the challenges of external heat buildup, internal heat generation poses a significant threat to the aircraft's electronics. At hypersonic speeds, the extreme temperature levels don't just affect the aircraft's structural integrity, they also impact the electronics and systems aboard the craft. These systems, including avionics, sensors, and communication devices, are susceptible to heat-induced failures if not adequately protected. For instance, in a hypersonic test flight, overheating in the navigation and communication systems could result in a loss of control or vital data transmission errors. While current technologies like heat-resistant semiconductors and liquid-cooled electronic enclosures are used in high-performance military aircraft, these solutions may not be sufficient when dealing with the extreme temperatures of hypersonic flight. The high thermal environment could lead to system failure if cooling mechanisms are overwhelmed. Internal cooling for critical systems such as flight control computers, propulsion systems, and cockpit instruments must be robust and continuous. Some researchers are exploring the possibility of embedding micro heat pipes within the aircraft to transport heat away from sensitive components. These micro-cooling systems, powered by capillary action, would help prevent the overheating of electronics, ensuring that the aircraft's critical functions remain intact. But even if we overcome this issue, there's still more to be done. Practical limitations and other hindrances. While the appeal of traveling at Mach 5+ speeds is undeniable, the design constraints necessary to achieve hypersonic velocities create a host of challenges for scaling these aircraft to accommodate larger numbers of passengers. Currently, most hypersonic designs are built to accommodate only a handful of passengers, no more than 10. This limitation stems from the aerodynamic, structural, and thermal protection requirements. The design of hypersonic aircraft today is driven by the need to balance extreme speed with efficiency. As a result, the number of passengers these aircraft can carry is severely limited. One of the primary reasons for this low seating capacity is the need for weight reduction. Hypersonic flight requires incredibly lightweight materials to reduce the stress on the aircraft and allow it to achieve high speeds. The use of advanced composites, such as ceramic matrix composites or CMCs, helps reduce weight but also limits available space for a full passenger cabin. Every kilogram saved translates into an increase in speed and fuel efficiency, but it also limits the aircraft's ability to fit more seats. Moreover, the aerodynamics of hypersonic flight dictate that aircraft are streamlined to minimize drag and maximize speed. A larger, more spacious cabin would introduce unwanted drag and turbulence, reducing the aircraft's overall efficiency and potentially compromising flight stability at extreme speeds. Additionally, hypersonic aircraft require advanced thermal protection to shield the structure from the intense heat generated by friction at speeds beyond Mach 5. The thermal shields that encase the aircraft's exterior take up considerable space, further limiting the room available for passengers. The most significant issue when scaling up is the thermal management problem. As an aircraft's size increases, the amount of heat generated by friction also grows exponentially. A larger plane's surface area results in more heat buildup, and the heat dissipation systems may no longer be sufficient to manage the added thermal load. This could require even more sophisticated thermal protection systems, which would further increase the complexity and weight of the aircraft, making it less efficient. Another key issue when scaling up is the structural integrity of the aircraft. The stresses placed on the aircraft during hypersonic flight are immense, and larger aircraft would experience more strain on their fuselage, wings, and overall frame. While advanced materials such as titanium alloys and ceramics help, they are still not perfect solutions for managing the combined heat and structural forces encountered at hypersonic speeds. These scaling issues contribute to the commercial viability challenges faced by hypersonic aircraft. Larger planes with more seats face increased costs for not only thermal protection and weight management, but also for design and construction. These complexities make the prospect of scaling hypersonic travel beyond a small niche unfeasible in the near future. All of this translated to limited seating capacity. This poses significant economic challenges for the commercial viability of these aircraft. Then there are safety issues. At hypersonic speeds, the challenges for pilots, crew, and the aircraft itself become exponentially more complex. At speeds exceeding 4,600 miles per hour, the kinetic energy involved is immense, making any malfunction or system failure potentially catastrophic. The aircraft would cover vast distances in mere minutes, drastically reducing the time available for pilots to react to issues. Traditional emergency systems, such as parachutes, are not viable due to the extreme forces at these speeds. Moreover, the aircraft's control surfaces may fail to operate as expected, making it vital for the aircraft to have highly reliable systems and fail-safes to prevent disasters. Additionally, the friction-generated heat at such speeds can damage the aircraft's structure, further complicating emergency situations. To address these challenges, entirely new safety protocols and emergency response systems must be developed. Traditional aviation standards are insufficient for hypersonic flight, requiring new guidelines for operations, emergency procedures, and certifications. This includes the need for specialized systems to manage unforeseen malfunctions, extreme weather, and emergency landings at hypersonic speeds. Rigorous testing is crucial, including simulations of malfunctions and testing of the thermal protection systems. Furthermore, the development of new certification processes, pilot training programs, and testing for safe landing protocols are essential to ensure that hypersonic aircraft meet safety standards. These tests and procedures are necessary for clearing hypersonic aircraft for commercial use, ensuring that they are as safe as possible in the face of the extreme conditions they will encounter. But let's say that a hypersonic aircraft becomes a commercial reality. What then? The last time something like this was tried, things did not end well. The Concorde, a groundbreaking supersonic passenger aircraft, revolutionized air travel with its Mach 2 speed, cutting flight times in half and offering a luxury travel experience. However, its high operational costs, limited seating capacity, and environmental concerns, including the disruptive sonic boom, made it unsustainable for mass commercial use. Despite its innovations, the Concorde's economic inefficiency, reliance on fuel-heavy turbojet engines, and restrictions on flight routes due to noise pollution confined it to an elite clientele. Its retirement in 2003 marked the end of an era, but its technological advances laid the groundwork for the future. Speaking of the future, China's Nankiang No. 1 aims to surpass the Concorde by achieving speeds of Mach 6, over 4 times faster than the Concorde. These aircraft utilize advanced propulsion systems and materials to address issues such as fuel inefficiency and heat resistance at extreme speeds. The Nankiang's ability to potentially reach low Earth orbit highlights the shift towards point-to-space travel, further expanding the possibilities of air and space travel. With improved fuel efficiency, higher passenger capacities, and more competitive pricing, hypersonic jets are poised to make faster, more economical long-distance travel a reality, overcoming many of the Concorde's limitations. But is that all? Well, not if you take geopolitics into context. Practical military applications and other global implications. Hypersonic technology holds profound potential to reshape several sectors, including military strategy, scientific research, and space exploration. As nations like China, Russia, and the United States race to develop hypersonic capabilities, the implications for global power dynamics, international security, and technological development are enormous. The arrival of hypersonic jets, such as the Nankiang No. 1, could serve as a catalyst for dramatic shifts in how countries approach defense, trade, and global cooperation, as well as introduce unparalleled advancements in commercial travel. At the heart of the global competition for hypersonic technology lies its military applications. Hypersonic weapons, capable of traveling at Mach 5 and beyond, can vastly alter the balance of power on the global stage. These weapons are far harder to intercept than current missile systems, as they can maneuver at high speeds, penetrate defenses, and strike with incredible precision. One of the most critical aspects of hypersonic weapons is their ability to travel through the atmosphere at extreme speeds, much faster than traditional ballistic missiles, which makes them difficult to track and intercept. One specific example of military applications is China's Hypersonic Glide Vehicle, or HGV, part of its rapidly advancing military hypersonic program. In 2021, China demonstrated a hypersonic missile that circled the globe before descending toward its target. The ability of such weapons to travel at high altitudes while evading tracking systems has profound implications for defense strategies worldwide. Hypersonic weapons, like the DF-17 missile system, could be used to strike critical infrastructure or military bases with precision. A specific military application of hypersonic technology involves potential use in the Taiwan Strait conflict. As China's military ambitions continue to expand, the use of hypersonic weapons could dramatically change the calculus of any potential invasion of Taiwan. Hypersonic missiles, with their ability to bypass conventional defenses, could neutralize key military assets such as aircraft carriers, radar systems, and missile defense batteries. The US military and its allies would face a considerable challenge in countering such fast-moving threats, which could alter the balance of power in the region and raise the stakes of any conflict over Taiwan. Additionally, these hypersonic weapons could enhance China's ability to deter foreign intervention by effectively targeting bases in the Indo-Pacific region. Moreover, hypersonic technology could serve as a counter to the United States' dominance in military technology. China's investment in hypersonic weapons is part of a broader strategy to develop technologies that can neutralize the U.S. aerospace superiority. With the US military focused on next-generation defense systems like the Hypersonic Long-Range Standoff Weapon, or LRSO, and hypersonic air-to-surface missiles, the race to develop these technologies has turned into a critical aspect of future warfare. But should we be hostile to technological advancement as a whole? Well, no. Hypersonic technology has the potential to revolutionize global logistics, trade, and international collaboration. By dramatically reducing delivery times, hypersonic jets could transform industries like technology, pharmaceuticals, and automotive manufacturing, while also improving the efficiency of humanitarian aid during crises. As hypersonic travel becomes integrated into global infrastructure, it could foster new forms of international research and collaboration, particularly in fields like space exploration and climate science. Additionally, the faster travel enabled by hypersonic jets could transform global air travel, making long-distance flights more efficient and opening up new opportunities for international business, tourism, and diplomacy. Well, that's it for now. Thanks for watching. Did you like this video? If you did, please consider liking, dropping a comment, and hitting the subscribe button so that you don't miss out on our new uploads. Also, don't miss this video you see on your screen right now. It's truly unbelievable.